This meeting is being recorded.
Yeah, so I will be talking about homotopy properties of Morse functions on non-orientable surfaces. It is a joint work with Sergei Maximenko, and he was my supervisor during my PhD program. And I will start and recall definitions of stabilizers and orbits. And so we have M, a smooth compact two-dimensional manifold which can be disconnected and have a non-empty boundary, and P be either a real line or a circle. And we consider DMX the group of diffeomorphisms of M fixed on a closed subset X from M. So there is a natural right action of the group DMX on the space of smooth functions, C infinity MR. And it is defined by the rule. We take H from DMX, F from infinity functions, and it goes as a composition FH. So the stabilizer with respect of this action is a set H from DMX such that this composition FH equals to F. So it's F preserving diffeomorphisms of M. And the orbit is just compositions FH for all H from DMX. We endow the spaces DMX and C infinity with Whitney C infinity topologies. Their subspaces stabilizer and orbit with induced ones, and also introduce OF as space component of orbit containing F. Now I'll introduce a wide class of groups which consist of Morse functions and generalize them. So it's the class FMP that satisfies two conditions. The function f takes constant value at the boundary and has no critical point in it. And the second is that for every critical point of f, there are local coordinates in which f is a homogeneous polynomial without multiple factors. So we see that Morse map, which is a subset of this class of groups. So the talk will be devoted to the precise algebraic structure of fundamental group of orbits of the functions on non-orientable surfaces. And I'll start with the result of Sergei Maximenko, and it's about reducing to the several cases on disks, annulus, and Möbius bands. So he proved that if M is a compact surface with a negative L characteristic, then for each function from FMP, there exist mutually disjoint F-saturated subsurfaces, Y1, Yn from M, each containing critical points of F and having the following property. Each Yi is either a true disk, annulus, or a Möbius band. And P1 of the orbit, it is isomorphic just to the direct product of P1 of orbits on each of these components. And each of them is either a disk, annulus, or a Möbius band. So for any surface, we need to understand what's going on this two disks, annulus, and Möbius bands. And the case of two disks and annulus was proved by Sergei Maximenko. The case of torus was proved by Feshchenko. Möbius band is considered in this talk, and Klein-Bottle was proved by Bogdan Major. Sphere and projective plane are still open problems. So, to explain the result, I recall the definition of Res products. So let A be a group, n is an integer number, and we will denote by Res product of A and Z a semi-direct product of A, n, and Z with respect to the natural action of Z on A to the power n by cyclic shifts of coordinates. So it's the following semi-direct product where homomorphism phi is defined by the following formula. For integer k and sequence a0, an minus 1, which cyclically shifts them as a k mod n, a n minus 1 plus k mod n. So, in other words, a Res product is a Cartesian product of a to the power n times z with the following operation. So, a0, a n minus 1k, b0, b n minus 1l equals to a0 bk, a1 bk plus 1, and so on. And the last is k plus l. So k shifts the sequence of b. Okay. And also notice that Res product with index 1 is just a direct product with that, and if the group is just trivial, then it's just that. So the result obtained by Maximenko was the following: that precise algebraic structure of P1 of the orbit for the cases where surface is not sphere and torus. Then we have that this fundamental group belongs to the class G. And class G is the following class, which is the minimal class of groups satisfying the following conditions. That trivial group belongs to this class, that if we take any two groups A and B, then their direct product also belongs to the class. And if the group belongs to G, and n is some integer number, then Res product also belongs to G. So it covers situations for oriented surfaces, and the situation of torus was considered by Bogdan Feshchenko. And now we should concentrate on what's going on the Möbius band, which is our joint result. So to explain it, I introduced modified Res product. So let G and H be groups, M is integer, and gamma is automorphism of order 2. Define the automorphism from G to the power 2m, it's important that it's 2 here, times H to the power m in itself by the formula. So it's similar to the usual Res product, but here we have 2m elements from G, and automorphism shifts the H0 So we have such equation. And this automorphism generates homomorphism from Z to G to M times HM, and the corresponding semidirect product is a modified res product. So in other words, modified res product is a Cartesian product G to M times HM times Z with the following operation. So this look on this formula. Yeah, so as previously, K shifts cyclically elements D, and gamma switches elements from E. So our main result is the following, that if M is a Möbius band, then for every F from this group, there are two possibilities. First is that there exist groups AGH from G and automorphism gamma of order 2 and number M such that fundamental group of the orbit is isomorphic to A times res product of GH gamma MZ. And the second case is that there exist groups AG from G and odd number B such that it's just direct product of A and usual res product with index B. And now I will explain how to see what these groups are on the Möbius band. So one of our previous results was that if M is a Möbius band and F from class FMP, then there is a unique critical component K of some level set such that if W is an F-regular neighborhood of K and Y0, Yn are connected components of closure M without W, where Y0 is annulus, which contains the boundary, then Y0 is always annulus and Y car are always disks. So this, for each H from stabilizer, union of these disks is invariant. So let us consider the set of all of these two disks. And since it's invariant with respect to the stabilizer, we have a natural action stabilizer on the set of disks by permutation. And also we can fix orientation on each disk and denote Y with hat a set of disks with orientation, and then we can extend this action on this Y with hat. Yeah, so then we can consider QF, the normal subgroup of stabilizer consisting of diffeomorphisms preserving each disk with its orientation. And the result that we obtained is that the quotient group of stabilizer with QF is isomorphic to a finite cyclic group, ZB, for some B. and its action on y hat is 3.
Irina, I'm sorry to interrupt you. Just a reminder, you have 4 minutes according to the schedule. Yes.
Yeah, I'll quick here.
Yes.
Thank you. Yeah. So we have that our cyclic group permutes disks, and the length of the orbit of a generator is b. So we have two cases. First case is where b is even, so let it be 2m, and in this case we have two situations. The disks can change its orientation or not. So we denote by d disks that don't change its orientation, and the length of its orbit will be b equal to m. So we have that all disks we can illustrate in this table, where d are disks preserving orientations and e changing. Yeah, so in this theorem, these groups G and H are products of groups where we take one disk from each orbit. So G is just product of disks that don't change orientation, and E that change. And group A is just a fundamental group on the analysis. And the second case is where B is odd. Then we have just usual rest product. And here we just take one disk from the orbit. And it's direct products. So several examples in 2 minutes. So here we have one disk, and on the Möbius band, and it can change its orbit. Let it have a degenerate point here. So its group will be Z. And cycle is 1, so here is 1. So the next example, here we have a generator which goes like that. So here we have that each disk is fixed. So it's just this group. And in this case, we have that orbit of this, that this disk can, on the Möbius band, go to this one. So these two disks are on the same orbit and correspond to this Z. And this disk can go to itself with changed orientations. So it's Z here, and the same for this disk, so it's Z here. And the last example, here generator goes this 2 squares, and so these disks has orbit 6. 1, 2, 3, 4, 5, 6. So it corresponds to this Z, and these two disks are this Z times rest product. And B equals 3. Thank you for attention.
Yes, thank you, Irina. It was a very interesting presentation. Thank you for your speech. So maybe someone wants to ask something.
Can you show 9th slide once again? I want to ask.
9th?
9th and 11th.
11 here? Or 9 first?
And 9th, yes. is can be elements of this group linearly ordered? If it's can be linearly ordered, it's
I didn't think about this question.
It's intermediate class of groups that whose elements can be linearly ordered between intermediate class between locally indicated group and infinite group. So it's maybe important in geometry, and in one place you have write direct product without brackets. Is it right? It's next slide. Direct product without brackets, but I thought.
What do you mean without brackets? I didn't think about linear orders on this.
Linear order. It's you can produce order, and the function of elements on number of a natural number, set of natural numbers, and you can order. But in this case, I think no, because you have element of finite orders when you take one from Z and G and H finite. So I think it cannot be linear order because if such an element exists.
Yeah, maybe I can't answer it right now.
Thank you.
Okay. Does anyone have some question?
Excuse me. I have a question. Which is a kind of stupid and general questions. Maybe we are discussing homotopy types of spaces of Morse functions or functions with isolated critical points on surfaces, right?
Yes.
Yes. I want to know, are there any studies on homotopy types of smooth function which may have non-isolated singularities such as Morse bot functions related to this?
For Morse bot functions.
Yes, space of Morse bot functions and some general functions. Related studies? Are there any?
I didn't work with it, but I don't sure. Maybe there are some results on this, but it's not connected with this topic.
Maybe
let me comment. If you don't mind, let me comment. So, is this in this situation when we have finite number of critical points and they are isolated and of specific type, then these functions, the orbits of these functions constitute a submanifold, Fréchet submanifold of finite codimension in the space of all functions. And then the result by Sergera, Francis Sergera, it allows to prove that there is that the map into the orbit from diffeomorphism is a locally trivial vibration. And so this allows to make homotopy theory. So we have a long exact sequence of homotopy groups of the stabilizer, orbit, and diffeomorphisms. And we know what are diffeomorphisms. We know that the stabilizer are either contractible connected components or a circle, and this gives some information about orbit. When we have functions, they have infinite codimension. So it is more complicated to study them and to work with them. To at least we need in order to make at least to understand the orbit of Morse bot function, we need result of that kind. Like Sergera, but it is more complicated because they have infinite codimension. That was the problem.
Thank you.
But Bogdan Fishenko, he has maybe I don't know if he mentioned that in his talk, but he is working in this direction.
Yes. Thank you.
Welcome.
Okay. So does anyone has more question? No. Okay. Thank you very much, Iryna. It was a very interesting presentation.